Hello everyone, we're going to go ahead into our third section, and our learning goal is actually going to be centered around partial pressures for gases. Now I realized when we left class the other day, I actually had mixed up on the problem that we were going to go ahead through, but we're going to talk about a couple of examples in here that should hopefully make it a little bit clearer as to what's happening and why it's happening the way that it does. So our goal is just to be able to calculate the partial pressure and understand how partial pressures work in a system. Now, if I have a mixture of gases in a container, there's a total pressure that's actually being exerted. Usually we'll measure it using, like I said, a manometer or something like that, but that'll show us exactly how much pressure is inside. Now, what if that's a mixture of many different gases? Just like the air that we breathe in is argon and oxygen and nitrogen and carbon dioxide and all these different things. There are lots of different gases mixed in there, and we should be able to figure out how much pressure each of them is exerting instead of just looking at, well, also, sorry, looking at the total pressure that's being exerted by all of those gases. Now, looking at the container we have here, we note that we have one gas that's in there and is exerting a certain amount of pressure, whereas we have a second that's exerting its own amount of pressure. When we mix the two, because remember our gases are able to be mixed easily, we'll note that the pressure increases for the total thing. Now, the total pressure should be the same as adding the pressure that was exerted by gas A, I'll call this one gas A, also with gas B. Okay? Now, in terms of our math, how are we going to figure this out? Well, to do that, we need to understand how many moles of each gas we have. Let's look at the following exercise. We have our two containers, different volumes, different amount of pressure, and they're joined by this, what we call a stopcock, or I forgot a way to say it, sort of a spigot, I guess you could say. Now, we're noting that they're containing, has helium, or sorry, both of them have helium, but it's at 45 degrees Celsius. After the valve is open, what is the pressure, sorry, of helium gas? The thing that we have to consider is, yes, we have the amount of pressure that they're under, but the thing that changes is now the amount of gas and the size of the overall container. That's something that we have to keep in mind. So while this one was 3 liters at 3 atmospheres, this one 2 atmospheres, 9 liters, when we join them, so when we open up this spigot, we now have a container that's 12 liters large, or the size of 12 liters. So we would have to readjust our pressure according to that fact. So let's take a look at what we have here. Now, what actual law are we going to use? Well, we're going to use the ideal gas law, because we have pressure equals, we're going to have the number of moles, we're going to have the number of moles, at this time we don't, over V. This is going to help us to see what the change is going to be. Now, if we're going from the, if we're going from the basic, actually we can do this one just using boils, because the temperature doesn't change and we don't know the number of moles. So we're actually going to go PV P1 V1 equals P2 V2. If my initial pressure was 3 atmospheres and the volume 3 liters, we're trying to find out what the new pressure is going to be, so P2 in a container of 12 liters. Divide both sides by 12. So 9 divided by 12 would be our actual answer that we would actually pull in. We could do the same thing for the other side. We have our pressure, our initial volume. We're going to change that and then see how it would affect the overall. Now, once we did that, we would add up those pressures, and that would actually give us our total pressure for the system. Similar situation to what we have here. And what I want you to actually do is, I want you to go ahead and pause the video right here. And I want you to try to calculate. It says we have 27.4 liters of oxygen at 25 degrees Celsius and 1.30 atmospheres. We also have 8.5 liters of helium at 25 degrees Celsius and 2 atmospheres. They're both pumped into a tank that now we have a volume of 5.81 liters. What is going to be the new pressure of oxygen, helium, and then we're going to add those together to figure out what the pressure of both gases are. Go ahead and pause right here, and in a moment we're going to actually start with what we need to do. Now, taking a look at what we're dealing with here, we're actually going to make a little bit of a change, remember. So let's take a look at what our new pressure is going to be for oxygen. You want to check your work at this time to see if you were correct as far as your answer. Now, after making the change from 27.4 liters to a smaller container with a, we're going to see, or we should see, sorry, an increase in the pressure. Is that what we see here? Yes, as we go from 27.4 to 5.81, same temperature, the pressure jumps from 1.30 atmospheres to 6.13 atmospheres. So it's a nice big jump. Now, what about for our 8.50 liters of helium at 2 atmospheres, now changing to 5.81? What should we see in terms of the relationship? Well, we have 8.5 liters going into a smaller container. So that means that we should also see an increase in the pressure of helium. In this case, we go from 2.0 atmospheres to 2.93. So some of these things, the thing I want to point out to you is, if you understand the relationships of how it works, it'll give you an idea of what is going to happen or why it's going to happen even before you do the calculations. Now, how we come about going to get our total pressure? Well, it's just as simple as adding our two partial pressures together to 9.06 atmospheres. Now, if you're within 0.01 up and down, you should be fine depending on how you round it, but it's not much of a problem. Now, this ends our partial pressure portion of the video. The last thing that we have to do is we're going to talk about effusion and diffusion. Sounds very, very close. Some of them you probably are very used to, but we'll get to that in the next video. Please write down your questions, leave a comment in the in response to the video, something you need assistance with, or any questions that you have, and we'll talk about this a little bit later. Have a good day.